So I've given, rather Arnav already had a copy of that chapter I wanted to circulate. So he'll pass it on to you guys, huh? And I've tried to make the chapter pedagogical, so it hopefully you can work through it and sort of at a reasonable. It's not at a very intense pace or anything, huh? Okay, are there any questions from yesterday, or should we now move on to the phase separation problem? Any remaining questions from yesterday? Okay, so in that case, let's move on. Today I am going to look at section 3, which is phase separation. Let me just sort of be more specific. I am going to look at what's called Kawasaki spin exchange kinetics. Okay, so this is the conserved analog of Glauber kinetics, and once I tell you how it works microscopically, it will become clear to you why it conserves this thing. Okay, so let me just remind you of the problem. You have a phase diagram. That's, let's say, the phase diagram of an oil and water mixture. That's the fraction of oil, which ranges from 0 to 1, and on this axis you have the temperature, and there's this coexistence curve basically, and the coexistence curve has a critical point which is symmetrically located in the Ising model. That's located at a critical value of the composition, which is just half. So if you have half of oil, you have half of water, and Tc. So that's the critical point, and here you have the homogeneous phase. Here you have the phase separated state down here, separated state, and the kinetics of phase transition problem is the following. You start up there from the homogeneous state, rapidly quench into the phase separated state. The system will now segregate into components. This is called the lever rule. They will segregate into these two components basically. One phase which will have be oil rich, and one phase which will be oil poor or water rich basically. Okay, and we want to study the kinetics of the phase separation. And the way one models this at the Ising model, at the Ising level, is the following. So this is what I'm going to sort of discuss for the next half an hour or so. So you have your usual lattice. Consider a site I with spin Si and a site J with spin Sj. Okay. So again, no intrinsic dynamics because it's an Ising model and the Poisson bracket of the spin variables is 0, but you basically put it in contact with a heat bath, and the heat bath sort of maintains the entire system at a temperature T and drives stochastic fluctuations into the system. And Kawasaki proposed that the right simplest one would be an interchange of nearest neighbors pairs Si and Sj. Okay. So Glauber had a spin flip kinetics. This is now a spin exchange kinetics, where you just interchange Si and Sj from nearest neighbor sites basically. And it sort of should be obvious to you that if Si plus 1 denotes A atom and Si minus 1 denotes B atom, this preserves the number of A and B atoms in the process. So that's built into the kinetics. Okay. So this is also goes under various it's was first put out by Kawasaki. So Kawasaki is a rather well known name in statistical physics. I mean, especially in theories of critical dynamics and so on and so forth. He also popped up in this earlier paper, this result of Ota, Jasno and Kawasaki. So this is also credited to him. It also gets called, for obvious reasons, spin exchange kinetics. Okay. So again, let's try to sort of frame the problem. mathematically. I start with an initial probability distribution. So again, I'm going to write down the master equation, though I won't get into such details of the calculations as I did last time. So you start with a probability distribution, which is P as a function of the spin configuration at time t equal to 0. Okay? And then you ask how this probability evolves, and the way the probability evolves is the following. Let me consider two, so you have this phase space of spin configurations. Let me focus on a state Si and a neighboring state Si prime, and Si will be just S1 at 1, S2 at 2, all the way up to Sn at site n, and the neighboring state will be S1 at 1, S2 at 2, dot dot dot, and an interchange. I'm going to consider interchanges. Let me sort of stick with the notation in my board. So I'm going to consider an interchanged configuration with Sk sitting at site j, Sj sitting at site k, and the rest of the spins all the same Sn. Is that clear? So the target configuration is just S1, S2, Sj all the way up to Sk, and here the nearby configuration is just a spin exchanged from there basically. So it's sort of obvious though it's going to become a little more lengthy in terms of writing down, but the evolution of the probability distribution of the sort of state I consider, del p by del t, is going to be a gain term and a loss term. The gain term will arise from a transition probability, so that's going to be with a minus sign. So a transition probability of starting off with the state Si, which is that state out there, and spin exchanging to a state Si prime, which is the nearby state, right? And that will be multiplied by the probability Psi t. Of course, I can pick any pair of nearest neighbor spins and sort of interchange them. So I have a summation over, let's say I'm exchanging the spins j and k. So I have a summation j is equal to 1 to n. That's the total number of spins, and k is summed over the nearest neighbors, which I denote as Lj. Is my notation clear? Because we have to get the starting point clear. Huh? Okay? So that's the target state. So that's the loss term for leakage of the probability. And let's bring this minus sign out here. Yeah. Let me just write down the complete equation and then I'll answer your question. Okay? And then the gain term is simply the transition probability or rate of flipping from a nearby, not flipping this time, exchanging from a nearby state Si prime to the target state Si. So that's obviously written the other way around, and the probability of Si prime t. And again, you can do this for any pair of nearest neighbors. So you sum j equal to 1 to n, and you sum k over the nearest neighbors. In Kawasaki exchange, you only allow the nearest neighbors to exchange basically, okay? And you sum over the nearest neighbors of j, and that's the gain term. So let's put that in a big box, because that's going to be the starting point, though I won't, as I said, get into such details of the derivation as I did for the Glauber kinetics. Yeah. Now it's clear? Okay. So again, that's your target state. You can escape from there by flipping there, by exchanging to that state, and you can enter the target state by flipping, by exchanging from that state, basically. Okay? And of course, you know the rules. If you want to go to equilibrium, the transition probability must satisfy the detailed balance condition. So the detailed balance condition is simply W of Si going to Si prime, the P in equilibrium of Si must equal to the rate of Si prime going to Si and P equilibrium of that, right? So basically in detailed balance, the number of systems in the ensemble going from there to there are the same as the number of systems going in the other direction, so equilibrium is maintained. By the way, I mean, just as a sort of general observation, let me share my sort of own experience. It's hard to remember these equations mathematically, but if you think of them physically, it's pretty clear what the equation is going to be. Okay, so have a physical picture in your mind and then write down the corresponding equation, then rather than just try to write down the equation directly. Okay, and again you can pick. Okay, so you can pick any transition probability for which satisfies detailed balance, and the appropriate transition probability I've been working with is the Suzuki-Kubo form, which is 1 minus tan hyperbolic beta delta H, which occurs due to the spin exchange, divided by 2. Okay, so this is what I call the Suzuki Kubo form. So it's exactly the same framework as before, and all that's happening is the stochastic move is now a spin exchange which conserves the composition of the mixture, basically. Okay, let's calculate this change of energy. It's a sort of a useful exercise to do. Let's calculate the change in energy. So you start off with the Hamiltonian of a spin configuration Si. That's equal to minus J sum over nearest neighbors Si Sj, and now of course there's no magnetic field in the problem, basically, right? Because now you're not fixing your magnetic field, you're fixing the concentration, as a matter of fact, basically. Okay, so the H initial, once I write it down again, it will become clear why I've written the expression. Now I'm going to isolate out the Sj and Sk terms which are interchanging. So the terms going with Sj are the sum over the nearest neighbors Lj, not equal to k. So I'm leaving out the kth spin, Slj. Those are the terms, all the terms which involve Sj, and all the terms which involve Sk are minus J Sk, the nearest neighbors of k, which is Lk, not equal to J. I am deliberately leaving out those terms where the two spins are involved, basically, and then I'll separately write that term down, which is minus J Sj Sk plus not higher order, plus all other terms in the system which are unaffected by the interchange. Okay, so again, just to reiterate, I am interchanging Sj and Sk, and I have isolated the terms from Sj and Sk, basically. Okay, after the exchange, what is the energy? After the exchange, the energy is simply minus J. At site J, you now have Sk, because you've interchanged the spins, and this term is still the same. These spins have not been changed after all. So, these stay the same, SLJ. At site K, you now have Sj because you've done the interchange. So, that's minus J Sj, and oh sorry, I did write here SLK. And there you have Lk is not equal to J SLK, and this term is the same, Sj Sk, and then all the other terms are also the same because those terms are not participating in the interchange. Very straightforward. It's sort of not particularly complicated. Okay, and this gives you the final expression delta H is equal to Hf minus Hi, and if I just write that expression down, it's J. So, I have to subtract this from this. So, the first term is Sj minus Sk, Lj not equal to K, Slj. So, that is that term. Then I have that term which is minus J Sj minus Sk sum over Lk. I am not going to I am not going to work this out all the way, just get you started on the initial sort of steps of the derivation. Okay. So, that Slk not equal to J Slk, this term cancels with this term and all these other terms cancel also. Okay. So, that is the delta H which goes into the transition probability or the transition rate and comes into this Kubo-Suzuki, into this master equation evolution. Okay. I am now going to leave the next bit of algebra to you, but basically it is exactly the same as I did in Glauber kinetics. Okay. You compute the evolution equation for some Sn average, and for Sn average you compute the evolution equation by multiplying both sides by Sn, and then sort of you get a large scale cancellation of terms, and I am just going to write down the final results. So, maybe I will sort of say that there is, because this is Kawasaki exchange, it is a little harder to deal with, but it's sort of worked out very carefully in that chapter which Arnav is going to send you. So, you have a couple of pages of algebra, and then let me get to the last equation, which is del. So, the evolution of the magnetization with time t. The magnetization or the order parameter in this case is the density difference of the two species. So, the evolution of the magnetization with time t is equal to 1 over 2 tau s k summed over nearest neighbors of n, which you are looking at, sk minus 1 over 2 tau s q, where q is the coordination number of a site, Sn average, and then finally this is sort of maybe I should write this down for pedagogy, because otherwise it would not be complete, but it is a bit of a slightly messy term. 1 over 2 tau s k summed over the neighbors of Ln, expectation value of 1 minus Sn Sk tan hyperbolic beta j. Sorry about this algebra, but sometimes it is important to do it. So, tan hyperbolic beta j Ln not equal to k S Ln minus neighbors of k Lk not equal to n Slk. That is the expression. Okay. And finally, you have a expectation value at the end. I don't expect you to follow every last detail of every this thing on the board, but get the structure clear. Okay. Again, to reiterate, you start off with the master equation. That's pretty obvious. You put in the transition probability with this expression for delta H, do some manipulation, and that is the final equation you end up with. Okay. And it's a substantial equation, a little more complicated than the Glauber kinetics case. Not surprising, because the kinetics in this case is interchanging two spins. Okay. And this is exact so far. There's no approximations. Okay. It's exact, and it's not particularly useful, because if you actually expand out this Stanch term, then you'll have expectation value of S and Sk, then you'll have all sorts of powers and so on and so forth. So just like in the case of Glauber kinetics, it's a coupled hierarchy. Okay. Here's where you impose the mean field approximation. You now know how the mean field approximation works. You take the expectation value of that function, that large function, to be just the expectation values of the individual spins, basically. Okay.
So, the spin exchange thing, right? The conservation of these things, those are not there. These microscopic details are not relevant, at least to here.
No, certainly it is. See, this expression is computed for a spin exchange, right? The conservation comes from the spin exchange, because you pick one spin at one site, you pick one spin at one site and another spin at the other site. Say that's +1 and that's -1. When you interchange them, you still have the same number of -1s and +1s in the system. Okay? And of course, if the two spins you are interchanging are the same, then Sj is equal to Sk. So the change in energy is just 0, as you expect, basically. Okay? Fair enough?
Yes.
Any other questions? Huh? Okay, so the last bit of work then is to, yeah.
These exchanges are between very different lattice points?
No, that's an important point. In Kawasaki spin exchange, they are between two very nearest neighbor points. They always consider nearest neighbor. As a matter of fact, people have also considered the dynamics you said, global conservation, where you can pick a spin from here and pick a spin from here and interchange them. Okay, and that people find is the few papers there are of that show that's a weak conservation. Okay, it's like having no conservation, basically. So the nearest neighbor exchange mimics the diffusion process. If you want to really think of a metal, what's happening is basically the following. Certainly, okay, if you have a metal with, let's say, A on or you have oil water mixture B on the other side, it's certainly not quantum mechanically possible that A disappears from here, B disappears from here, and then suddenly they reappear at the other side. Okay. Usually in metallurgy, this process is mediated by a small number of vacancies that are in the system. Okay. So A would go into the vacancy, create a vacancy there, B would come into the vacancy, and so on and so forth. And a very small fraction of vacancies actually enable the exchange. Okay. Again, you should, I want to emphasize this point, that these are paradigms. They are not exact mimicking of what's happening at the microscopic level. Though people, including myself, have also looked at vacancy mediated phase separation. But that's not necessary. The physics is the same. Okay. Any other questions at this point? I hope you'll be able to do this algebra out in your hostel rooms. Let me then just sort of bring this calculation to a closure. Let me remove the exact from here. Let me remove the expectation value from here. And now I have expectation value here, 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 and here. Okay. So that's just 1 minute. Let me just write this down, then I'll answer your question. So that's a mean field evolution equation. It's now a closed form evolution equation for the magnetization field. Okay, it only depends on the magnetization at a site and the neighbors basically. Yeah.
You said we are looking at only exchange of nearest neighbors.
Right.
But in the expression for this initial and final energy,
Yeah.
we are just exchanging any IS and with KS between.
No, we are not. See, I'm isolating out the spins Sj. I'm isolating out the terms with this Sj and Sk, where Sj and Sk are nearest neighbors. Okay. Okay. So, sorry, I plotted this here. I'm just isolating the terms which are with nearest neighbors, basically. Which is why I left out this coupling between Sj and Sk. If I had put it into the summation, I would have had a double counting. Then I would have had to put a plus sign out there. Okay. That's why I left it out deliberately. Okay. Any other questions? Yeah.
Physical interpretation of each of these terms, like there are 3 terms in the
Yeah.
Is there, like, can one interpret them differently, physical interpretation of this term?
It's easier to say that in terms of a partial differential equation model, which I'll make the statement next. Okay, you can see what the 3 terms. So the linear terms will give instabilities, and the structure is again the same. The linear term will give instabilities, and the nonlinear terms will give saturation of the instabilities. Basically, I'm going to work this out for you. Don't worry. Okay. Yeah. Sorry.
S and SK, you can't keep the 2 body correlated. You could further make it like.
Well, then you would have 2 coupled equations.
Yeah.
Though they would be a slight little more accurate. Doesn't change the physics. Yeah. Doesn't change the physics. It's like this BBGKY hierarchy, as it's called, basically. Yeah. So here, this is the truncation at the first correlation level. Yeah. Yeah.
The parameter Q is like the coordination.
Yeah. So it's on a simple cubic lattice, it's just 2 times the dimensionality, basically. I mean, remember when you do mean field theory, the Curie-Weiss mean field theory, you find that the critical temperature is Qj. Okay. And that of course is wrong in 1D because it says there's a phase transition in 1D when there's not. It's also wrong in 2D because it says it's 4J. Whereas on Sagar's solution tells us it's 2.269J. But it's okay. And 3D, 4D, we don't know, of course, what the answers are. Okay? Okay, so any more questions? Again, not about every last detail, which I hope you will work through yourself, but about the general direction we take. Take it. So then, now you know how this game is played. So let me recover this little piece of the board out here, and so now I don't have an exact equation anymore. This is a closed form. So what do I have? I have a mean field evolution equation, which is a closed form evolution equation for the order parameter. Okay, and it involves its neighbors, etc. The last bit of work I do is to obtain the Cahn Hilliard equation. And for the Cahn Hilliard equation, I basically, so now we come to the Cahn Hilliard equation. The Cahn Hilliard equation is obtained by by coarse graining, identifying Sn as an order parameters depends on space and time. It depends on time because the system is a non-equilibrium system, right? In equilibrium, that dependence would go away, basically. And then again, and certainly I'm not going to go through this on the board. You do your usual Taylor expansions, your expansion around a center point, etc., etc. All that algebra is worked out in my article. I'm just actually going to give you the final answer, if you permit, because I want to spend a little time discussing the Cahn Hilliard equation. So I'm not doing the expansion out here. The final answer is 2 tau s. So now you have a partial differential equation, del psi by del t is equal to minus del squared Tc by T minus 1 psi minus 1/3 Tc by T the whole cubed psi cubed plus Tc by Qt. Well, A I have absorbed into the derivative, so that's A del square psi. Okay, that's the final equation, and that's what's known in the literature as the Cahn Hilliard equation. Of course, when you do the Taylor expansions, there are lots of higher order terms which are neglected in this expansion. Okay, so that's called the Cahn Hilliard equation. If you remember, we had encountered this name Cahn earlier also. So that's the Cahn Hilliard equation. Notice that superficially it's very similar to the TDGL equation, right? But actually it's vastly different. This was without that minus del squared was basically the TDGL equation. Okay, so it's going to have the same solutions as the TDGL equation. Homogeneous states will be 0 and plus minus 1. There will also be a kink solution of this. Okay, but you have this all important minus del squared operator sitting out here, which enforces the conservation law. Can somebody tell me how it enforces the conservation law? This extra del squared, it's sort of, what is the conservation law? Huh? The conservation law is that the integral of psi must be conserved. So, psi is the density difference of A minus B, and the requirement is that the integral of psi must equal at all times must equal the integral of this, which is the number of A atoms, minus the integral of this, which is the number of B atoms. Okay. So, if you have a 50-50 case, that is called a critical quench, then Na is equal to Nb, and this integral must be identically 0. Is that obvious from the equation?
Just irreversibility plus divergence of the.
Yeah, that's exactly the point. It's like it is a continuity equation basically. Okay, so if you just integrate both sides with respect to space, you will just get boundary terms on the right hand side, and the boundary terms are 0. Take it to be 0. So the integral of psi is a constant in time of the motion. Unlike in the TDGL equation, in the TDGL equation you didn't have this continuity equation structure basically. Okay. So, I am actually going to, that is the next statement I am going to make. The next statement I am going to make is, maybe I can get, maybe I will keep the phase diagram and I will keep the Kawasaki kinetics. Okay. Yeah. So, that is your master equation based derivation, but there is also a phenomenological understanding, a phenomenological derivation, and the phenomenological derivation says that this is a conserved quantity, so it must obey a continuity equation. Del psi by del t is equal to minus grad of some current, right? What is the current? The current is transport of material is driven by a gradient in chemical potential. This is on Sagar's sort of prescription for non-equilibrium thermodynamics. Okay. So, this is minus grad grad of a chemical potential. Okay. And this finally gives you the chemical potential is just interpreted as minus f over psi, where the functional derivative of that. So, that is del squared del f over del psi, where this is just the Ginzburg-Landau free energy. So that's the two-line phenomenological argument of how you get the Cahn Hilliard equation. I hope the steps are clear. Psi is a conserved variable, so it has to obey a continuity equation. That's the continuity equation. The current is the gradient of the chemical potential. If you want, you can put in, you should actually put in some diffusion, constant diffusion out there, and then the chemical potential is the gradient of the free energy. So that just gives you d del square del f by del psi, and this of course what you have in brackets is del f by del psi. Okay. So that's the argument that you go. Again, you now sort of rescale it into you rescale into dimensionless units, and let me write down the final form of the Cahn Hilliard equation, which people usually study. Del psi by del t is equal to minus del squared psi minus psi cubed plus grad squared psi. Okay. Let's put this in a box. And what you have in bracket is simply the corresponding TDGL equation term. The extra del squared comes from this one is 1 and this is the other basically. Okay. So that's where the extra del squared comes from. And this is the equation, the basic equation if you want to study. And obviously now the question is how you will study it. So if you want to do a sort of a numerical study of phase separation, one prescription at the microscopic level is to start off with the Ising model with Kawasaki spin exchange kinetics. So you start off with a random configuration of pluses and minuses and drive that via Metropolis or what, Suzuki Kubo, whatever you prefer, and that will give you blobs, phase separated blobs like they were in the picture I gave you. And the Kawasaki kinetics will ensure that your blobs add up to give the same area or volume that you started with. Okay. The other possibility is to start off with some initial condition out here and look at its stability analysis, and that's very easy, and that's what I'm going to do in my last 15-20 minutes basically. Okay. Okay. So on inspection it's clear that psi star equal to 0 plus minus 1 are solutions, right. As a matter of fact, any homogeneous psi is a solution. So maybe I should write that down also. So because of the extra grad squared operator, any arbitrary flat psi 0 is a solution. If you start off with an absolutely flat initial conditions, no fluctuations, that's it, you'll just sit there, okay, you won't go anywhere, okay. And additionally, psi sz is equal to tan hyperbolic plus minus z over square root 2 is also a kink solution. Because it's a kink solution of what's in the bracket. So obviously once that becomes 0, then an extra del squared will just leave it as 0 basically. Okay. So you have the same static solutions, except now you are seeing that any homogeneous psi 0 is a solution. In the TDGL, of course, only 0 and plus minus 1 were solutions. Okay. So now we are going to study the evolution after temperature quench. So that's the sort of quench I have done, but maybe we can take 5 minutes to answer any questions if there are any. Yeah. The kink solution is, forget about that for the moment, right? The kink solution satisfies this equation. So that just gives 0 if I plug it in there. and then del squared 0 is of course just 0. Okay. Anything that satisfies the TDGL equation is also a solution of the Cahn Hilliard equation. Additionally, because of the del squared, any homogeneous psi 0 is a solution. Okay. Any other questions? Maybe before I do the linear stability analysis, it's also useful to do some dimensional analysis of this equation. So, let us do dimensional analysis at this level. Basically, if the characteristic length scale is L, then dL by dt, which is the term on the left, just the sort of rate of change of the domain size, is proportional to a gradient of the chemical potential. The chemical potential is 1 over L, that is what is called the Gibbs-Thompson boundary condition, and the gradient gives an extra factor of 1 over L. Okay, just dimensional analysis of this equation. Okay, and obviously this integrates up to give LT goes as t raised to power 1/3. That is an important result in this field, and actually this growth law is far more universal than the Cahn Hilliard equation. It applies in all sorts of different contexts. This is called the Lifshitz-Liozov growth law. Okay. So, because it is more tortuous in this case, the growth is slower than in the TDGL case. There you had t raised to power half, here the exponent is t raised to power 1/3. Okay. I have not talked about hydrodynamic effects yet. Okay. I believe Rahul Pandit was here last week talking about hydrodynamic phase separation. Okay. That can speed up the exponent. If you have hydrodynamics turned on, then you get sort of regimes of hydrodynamic growth which are faster. Basically, the material gets pumped along interfaces by the hydrodynamic modes. Okay. But for diffusive transport, as we have out here, the growth law that applies is t raised to power 1/3, and in the previous case it was faster, it was just the exponent associated with the random walks, and this one is called the Lifshitz-Cahn-Allen growth law. Both of these growth laws are very, very ubiquitous. You see them in all kinds of growth and aggregation phenomena basically. Okay. And as you go on in your research, you will probably, I mean, if you are doing non-equilibrium studies, you will encounter them at some place or the other basically. Okay. The last thing I want to do is a linear stability of this equation. So, I start off, so let us do a quench. Now, if the quench is down the middle, then I have half of oil and half of water. Okay. And that means that the average order parameter is 0, Na minus Nb. On the other hand, if I quench somewhere on this side of the phase diagram, then I have a surplus of oil and a surplus of water, surplus of water and less of oil, right. So, there you have an asymmetric composition. So, that is where psi 0 comes from basically. Psi 0 measures how off critical the concentration is. Quenches at different places along different vertical lines correspond to different values of the overall composition psi 0. Okay. So, what I am going to do is the following. I am going to look at the, so I am going to look at the following initial condition. I start off with a homogeneous order parameter psi 0 everywhere plus small fluctuations. And I am going to ask what happens to these fluctuations as a function of time. Okay? Yeah, you have a doubt.
Yesterday you are deriving for the non-conserved system and KDT that is valid. And here we are deriving for the conserved case.
Right.
This is the difference. Na?
Yeah, that's the difference. The linear stability you're talking about, all this is for the non-conserved. I mean, this is all for the conserved case. It was, yeah, first 4 lectures we talked primarily about the non-conserved case. Partly, because all this sort of techniques carry over to the conserved case. Okay, you use the same master equation, you use the same coarse graining, you have the same static solutions, etc. Okay, so I sort of thought we should do that at length, and then I'll just sort of say this as an add-on. Yeah. So does that answer your question? Yeah. Okay.
Like in the global kinetics was easier to understand that LT was as t to the power 1 by 2 t was the base boundary, like the random mode.
Right.
But how can one understand this 1 by 3 power?
Okay. Firstly, I should say there's no rigorous argument for t raised to power 1/3. So you just have a scaling argument. This argument is due to David Hughes. See, okay, now that you asked the question, Lifshitz-Liozov in the 1960s considered the phase separation of a mixture which is highly asymmetric. There's almost no oil and only water. In that limit, they came up with an extraordinary solution of the phase separation problem, okay, and they find the growth law t raised to power 1/3, okay. But that was not for the 50-50 composition, which is of more interest to experimentalists. So Hughes actually generalized the argument by coming up with this hand waving scaling argument, and the scaling argument is simply that you do dimensional analysis on this equation. The left hand side is dl by dt. There's a gradient out here which is 1 over L, and then there's a surface, there's a chemical potential which is sigma over L, okay. That's on an infinite droplet, again the surface tension is identical, the chemical potential is identically 0, okay. And that's it. So you just take L squared up here, integrated. This is the Hughes argument. This is the level at which there is an argument. There is no better argument, okay. Well, not millions, but tens of thousands of experiments, yeah. But I told you that if you add on hydrodynamics to this problem, then you can get other growth laws also. These are well catalogued in that chapter which Arnab will be sending you, okay. Yeah.
Experiments are matching with this growth law, then the hydrodynamics is not relevant for the
No. So the way it works is, okay. So if you add on hydrodynamics, the hydrodynamics only kicks in at larger length scales. So in that case, you get a crossover. LT starts off as t raised to power 1/3, that's diffusive growth, then crosses over to t raised to power 1, I think, that's called viscous hydrodynamic, and then crosses over to t raised to power 2/3, which is called inertial hydrodynamics. So there's a crossover length scale associated with each of these. You're familiar with the phenomenon of crossovers, right? Exponent crossovers. So in that case, that's what you get. Huh? So if you're looking in the early stages in experiments, polymer experiments are very slow, for example. So almost the entire range of time you'll get t raised to power 1/3. But if you're looking at some oil and water phase separating, you would also see these regimes. And the crossover lengths are related with the Reynolds numbers and stuff like that, basically. Okay, yeah, but yeah, as I said, one doesn't want to sort of make things too complicated. If you just have diffusive dynamics in binary alloys, you would expect a Lifshitz-Liozov growth law. Okay.
So this is clarification. So although we have used Suzuki to go transition rate,
Right.
But I think it doesn't really matter to see these.
The constraint equation would be the same for any transition rate, which satisfies detailed balance because you have to drive it to equilibrium. Yeah. If you do it, the calculation is easier to do with Suzuki Kubo. In Metropolis, there's this discontinuity, right? It's e raised to power minus beta delta h if delta h is less than 0, or no, if it's greater than 0, and it's 1 if the delta h is less than 0. That's right, yeah. So that makes it a little painful, but it'll end up giving exactly the same result, and that's sort of apparent from the phenomenological argument. Okay. Okay, so let's look at the linear stability analysis fluctuations of psi around psi 0. What happens to them in time? Okay, so then you write down psi at any arbitrary time is equal to psi 0 plus delta psi r t, and we're going to do we are going to ask in linear stability. How does this go? How does this go in time? Does it grow exponentially? Does it decay exponentially? Okay. The same question I asked for the TDGL equation. Help me out, guys. You're all expert at this now, huh? So I'm just going to directly write down the equation. What is the left hand side? Del by del t delta psi is equal to क्या होगा बताइए? Minus del squared, the first term is psi 0 plus delta psi, ठीक है ये वाला, and minus psi 0 cubed minus 3 psi 0 squared delta psi, right, and the last term is grad squared psi, grad squared delta psi. Okay, I have just directly written the sort of linear analysis. Because psi 0 is a solution, obviously this cancels with that. Any homogeneous psi 0 is a solution. Okay, so that's your equation. It's minus del squared 1 minus 3 psi 0 squared plus del squared delta psi. Okay. Let's put that in Fourier space. Now you should be comfortable with Fourier transforming in your heads. Okay. So del by del t is of delta psi kt माइनस डेल स्क्वायर्ड का क्या आएगा? k स्क्वायर्ड, और इसका क्या आएगा? 1 माइनस 3 psi 0 स्क्वायर्ड माइनस k स्क्वायर्ड डेल्टा psi k t in Fourier space. So this is how the modes grow or decay, and this is the quantity I had earlier called gamma k, right? Let's plot gamma k for different values of psi 0. Okay, let's plot gamma k for different values of psi 0 out here. So let's start with psi 0 equal to 0. That's the case of a critical quench. Okay, critical quench means 50% A, 50% B. It's a symmetric mixture. Okay, and what does it look like? Somebody help me. So this guy is just 0, huh? So it's going to go up like that. There's a characteristic length scale. It will come down, and at k equal to 1, it will cross the axis. So all these modes are unstable. All these modes are unstable. Okay. Okay. So if you have linear fluctuations around a random initial condition with a 50-50 composition, they just that will grow with time. and domains will be formed, and finally the domains will saturate, and then domain growth will start after that. So first is the exponential growth regime, and then is the domain growth regime. Let's plot it for another value of psi 0. Now you're going to find a little twist out here, okay? Gamma k versus k, let's plot it for psi 0 equal to plus minus 1. Fluctuations around the fixed point of this equation, around a fixed point of this equation. Help me guys, huh? ये हो जाएगा -2 minus k squared. हाँ, yeah, minus out here and 2 plus k squared. So what is it going to look like? It will just be always negative. It's never positive. So in this case, all the modes will decay. All the any fluctuations of any wave vector will decay with time. Okay, that's not surprising. After all, you know the fixed point value is plus and minus 1. It's the same for plus 1 and minus 1. The funny thing that happens is the following. Let's consider psi 0 greater than 1 over square root 3. Okay, and I'm going to plot now gamma k versus k. Okay, so I'm looking at so strictly speaking, any psi 0 value, if you quench it deep enough, should phase separate according to this phase diagram. Okay, but let's look at the dynamics. Something interesting is going to come out. Help me plot this, huh? Psi 0 greater than 1 over root 3, yani ki this is greater than minus 1, minus minus again. So though thermodynamically the system would like to phase separate because there is a better free energy to be found by phase separating, dynamically there is no route for it to phase separate. All the modes decay. If you look at fluctuations around an average value of psi 0, where psi 0 is larger than that, or minus psi 0 is less than minus 1 over root 3, then the modes fluctuations will decay. Okay? अब क्या करें? How will the system get to its preferred equilibrium? I want to one concept from you guys, huh? जाना तो है भाई, you know there's a better equilibrium out there, you're going to get there. How do you do it? Huh? No, that's not the answer. You can't do it with linear fluctuations. You can't do it with linear fluctuations. You need a droplet of the preferred phase to form in the non-preferred phase. Okay? And that droplet has to be larger than a certain size. It's what's called a critical droplet. Pinaki is an expert on these things, and you must grow, then the critical droplet grows. Okay. So that's the statement out here, and this is the source of this spinodal boundary which I had drawn in a dashed line, this dashed line. And this spinodal boundary, it's not a phase transition boundary in nearest neighbor models, but if you quench into here, this region between the miscibility gap and the dashed line, the system would like to phase separate, but you have to kick it to make it phase separate. Huh? So the homogeneous state is a metastable state, and this picture that people always draw is a boy is rolling a ball on a hill or something, and the hill gets stuck in this, the ball gets stuck in this metastable state, right? Have you seen this before? Huh? And then the ball would like to, you have to kick the ball, if you kick it gently, it just sort of rattles around in the local minima. If you kick it hard, then you can get it over the barrier into the preferred global minima. Okay, that's the concept of this spinodal line. So metallurgists use the, or material science guys use the notation, use the nomenclature that if you quench below this dashed line, you have spinodal decomposition. if you quench into this region, then you have nucleation and phase separation. The late stages of nucleation driven growth are the same as those of spinodal decomposition. It's only in the early stages that the pathways are different basically. Okay. And again I emphasize that in usual models of statistical physics, this spinodal is only an artifact of the mean field. Okay. It's not a genuine phase boundary. Okay, I think I should take some questions at this point and then I should stop because I have to leave unfortunately. Are there any doubts? I've thrown I mean they're simple enough concepts, but I've thrown a lot of concepts at you, I hope. Huh? So let's answer questions. Huh?
At that point we saw that there is no phase separation happening.
At which point?
The last side not greater than 1 by.
Yeah, so if the asymmetry is greater than 1 over square root 3, I should say if the mod is greater than 1 over square root 3, okay, then linear fluctuations around the homogeneous state will not grow. That's the statement. Okay. However, the system thermodynamically wants to phase separate. Given infinite time, it will find a way of getting to equilibrium.
How we introduce that? We have to introduce some noise there in the equation or something?
You can introduce noise or you can seed it with droplets in the initial condition. Huh? I don't know, when we were kids, we used to do this experiment where we would have a supersaturated sugar solution and then we would grow mishri out of it. Has any of you done this experiment? That's it, that's a nucleus. The mishri is a nucleus. You put in a thread with some little crystal of salt or of sugar on it and then things grow around that. Huh? So you can seed it or you can give it thermal fluctuations basically. As long as the fluctuations have to be large enough to cross this, and this is a whole, these escape problems are a whole area of study in statistical physics basically. Obviously, intuitively it's clear that the escape time will depend on this barrier size.
That's the typical times.
Huh?
That's the typical times. I was about to ask that.
Yeah, that's the typical time scale, will depend on the barrier size. It will be some Arrhenius factor if you have noise. Otherwise, in quantum mechanics, it will just sort of tunnel through the barrier. So, there will be a tunneling time. If the barrier is higher, the tunneling will be higher. And I'm talking about the simplest systems out here. But as you go on, you will encounter things like proteins and glasses, etc., where you have a very nasty sort of heavily structured landscape with multiple minima, local minima and one global minima. And it might actually be impossible getting to the global minima. You just are stuck all your life in a metastable state basically. Okay.
It's possible to get to this reasonable time scale.
Reasonable is not a good way of thinking of it. At this boundary, the time scale diverges. Okay. So the time scale depends on the barrier. The barrier is lower and lower as you get closer and closer to the spinodal line. Okay. So the time scale tau, if this barrier is delta, then the time scale tau is e raised to power delta beta, and the barrier becomes 0 at the spinodal line. Okay. And that's how you cross over into spinodal decomposition. So again, if you hear those names in future, remember that spinodal decomposition out here, nucleation and growth out there. Okay. And nucleation is basically getting stuck in a metastable state and needing a big kick to get out of it. You know, these, I mean, in Delhi, there is a major pollution problem. You read about it in the newspapers and all that, I suppose. Huh? So there was this talk of cloud seeding. Cloud seeding is the putting of nuclei in those clouds. I think they use silver iodide or something to enable the phase transition, which allows the supersaturated vapor to convert to rain. Okay. Wasn't successful, but I mean, of course, the director of IIT Kanpur made some crazy statement like it was totally unsuccessful, but we learnt a lot from the experiment. So, yeah, so that's the concept of nucleation and growth. And of course, Pinaki studies these structural glasses the time scale of escape from the structural glass would prefer, correct me if I am wrong, would prefer to be a crystal thermodynamically. But because of its preparation, it's stuck in a metastable state, and the lifetime of that metastable state can be the lifetime of the universe. So, if you sit and watch glass convert to its preferred phase, you're going to have to be there a long time to do it basically. But sorry, I'm rambling. Any more questions? You should ask the questions. I shouldn't ramble. Yeah.
Did you make the claim that there is a critical size for nucleation?
How did I make the claim? That's not there in the linear stability analysis. Okay, you'll have to do a nonlinear calculation for that. Okay, I'll tell you how to do that nonlinear calculation. You do the same droplet experiment that I had done in the TDGL. Ask about a droplet growing in a background, okay, and that will give you a critical size above which the droplet grows and below which the droplet shrinks. Okay, that's the way to get that critical size. This is a, Sorry, you'll have to speak up, better. That is nucleation. So the droplet is the nucleus, and it has to have a critical size. You can't put in one atom and expect that that will drive the phase transition. You have to put in some amount. Some amount depends on how far you are, exactly like Arnab was asking, how far you are from the spinodal nucleation boundary, basically. Okay. Again, the length scale of the droplet you have to put in. The time scale goes to 0 here, and the length scale also goes to 0. Okay. At the spinodal boundary, it gets larger and larger as you go away, basically. Okay.
System is connected to the bath, then why it needs some extra push from?
No, it doesn't need some extra push, but if the barrier is high, it could take a long time for this Arrhenius factor to become relevant, right?
But according to this theory, suppose we have a droplet which is less than the critical size, then it will not grow. Is it correct?
Yeah.
So why it is?
No, sorry. Let me repeat. That's not there in this linear stability analysis. That statement. In the linear stability analysis, if psi 0 is greater than 1 over root 3, there is no linear fluctuations will not be destabilized. Okay. So, you need to put in a finite size droplet. How finite size depends on how far you are from this dashed line, basically. I hope the concept is clear. So, please do that same, that's what I answered him, do the same thought experiment of a droplet of -1 growing in the background of +1. You will find there is a critical size of the droplet above which it grows and below which it does not grow. Okay. Yeah.
If I replace in that phase diagram CA with psi 0, so 0.5 is like psi 0 equal to 0 point.
So the midpoint is psi 0 equal to 0.
And I have like this is spinodal line points at like plus minus 1 by root 3.
Yeah, that's right. That's the spinodal line.
So if I am inside that, I will phase separate.
I spontaneously phase separate. So this local this thing will not be there. The ball will just roll down the hill.
And if I am between the dashed line and the solid line, then I need
the ball will be stuck in a local minimum, or the protein or the glass or whatever will be stuck in a local minimum, and you will need to activate it out of there. Activation is again, as I said, a kick of some kind. Quantum mechanics it can be tunneling. Classical mechanics it can be from the heat bath. Okay.
Psi 0 greater than 1 by root 3 like means the concentration of one kind of species is more than the concentration.
That's right. So that's what I'm saying. If you quench down here for maybe I should have drawn this, but this is getting very busy. But anyway, if the quench is like this, then the composition is, let's say, 0.25 or something. So there's 0.25 fraction of A and 0.75 fraction of B.
Yes. I was asking if that is the composition, means like there is more probability for a bigger droplet to exist, like to form, because the compositions are like
No. That's not correct, because you're starting off from a homogeneous phase. You're just looking at fluctuations around a homogeneous phase. Okay. The droplet is a nonlinear structure which you have to introduce in there somehow by a fluctuation. Okay. It's not there in the linear fluctuations. Is that clear? Not clear, huh? क्या doubt है बोलो?
You don't have a droplet to begin with.
Exactly. You just have fluctuations around a homogeneous background, and those fluctuations will all decay if the asymmetry is large enough. Okay.
That encodes only the asymmetry in the initial homogeneous.
And then with the passage of time, there will be a fluctuation and you can have a growth of a droplet, huh? These spinodal lines shadow all lines of first order phase transition. If you recall my phase diagram of a magnet, which was in temperature magnetic field plane, let me just sort of draw this once again. This is 2, this is 1, this is up, and this is down, right? So I didn't talk about it at that time, but there's a spinodal boundary out here also. What does that mean practically? That means if you start off with all down spins, okay, you force your Ising model to be all down spins, and then you place it at a slightly positive magnetic field, where you know it would like to be all up spins. It's not going to go there spontaneously. There will be some residence time in the metastable state. Okay. So if you quench into that region out there, so that's the spinodal boundary. If you quench into that region out there, you will get, you'll have to develop a nucleus before the phase transition can take place. If you quench there, it just rolls down the hill basically. Okay.
What's the bound of the initial condition?
Huh?
It's a bound of some sort of a bound of the initial condition in the homogeneous side.
Exactly. Okay, any other questions?
So I have a very basic question. Suppose we'll take the free energy only Landau term without Ginsburg term. So can we see this phase transition? No.
Because in the Landau term, if you don't have the Ginsburg term, then you don't have any penalty for interfaces. Okay. So the interface, there has to be no annealing process of defects at all. You are perfectly happy being in one local minima at one point and another local minima. You need the surface tension comes from that gradient term, and that drives phase separation. Otherwise, you can live with an infinite density of defects, basically. Okay. Yeah.
To make the system stabilize for the psi greater than 1/3. So if we could add one more term from the approximation from the modified TGDL equation, if we could add one more term that has positive coefficient, that could also make the system stabilize.
Okay, there are two answers to your question. First is that if you add any higher power term, those would be even smaller in linear stability analysis. So they are not going to change the linear stability. Huh? The second is, in general, Landau theories with this is a Landau theory, it's called the 5/4 theory. I didn't give it that name, but it's called the 5/4 theory. If you have a 5/6 theory, etc., you can also have more complex phase transitions basically. And in a 5/6 theory, this one doesn't capture first order phase transitions. The 5/6 theory also captures first order phase transitions, etc. Just familiarize yourself little with Landau theories from ChatGPT or something, okay? You'll get there's a lot of problems modeled by Landau theory, okay?
Are there any more conservation laws because it's a higher order equation?
How do you mean higher order? It's no.
Numbers are conserved. That's one.
And are there some other functions of psi which are conserved?
Right.
Not that are known.
Okay.
Not that are known.
And they don't play much role in this kind of transitions.
That's right. Yeah. But yeah. The obvious one is the integral of psi. That's conserved. Yeah. Okay.
Okay, so if there are no further questions, so please join me to thank Professor Puri for giving us this